Hello students, today we will read dipole in uniform external field. We got a permanent dipole which we have kept in the uniform external field, and now we will see how it behaves in the field. So, we considered a permanent dipole of dipole moment P in the uniform external field E. The permanent dipole means a dipole which exists irrespective of presence of E. If E is present or if E is absent. In both the cases, dipole exists. In both the cases, dipole exists. Such a dipole is termed as a permanent dipole. Now, the figure states over here is, this is our dipole having minus q and plus q charge with a length of 2a is placed in a uniform electric field which is going in this direction. Uniform electric field going in this direction. Due to minus q, the force on minus q is in opposite direction. What is the value of force? Force is written as k q1 q2 by r square. How do we write electric field? We write k q2 by r square or kq1 by r square. This is due to q2, we will write q2. So here this value is not available, but other than that this and this is available. So these three can be replaced by E because E is equal to these three. So F equals to kq1. Here q1 is minus q, therefore F equals to minus EQ. Minus EQ. This is not K, this is E. We are replacing by E. Okay, so this is the force. Force experienced by a negative charge due to the presence of uniform external electric field. Now, at plus Q, this is the force in the same direction as the electric field due to the electric field. There is a force QE on Q and a force minus QE on minus Q. The net force on the dipole is 0 as explained in the previous class since E is uniform. However, the charges are separated, so the force acts at different points, resulting in a torque on the dipole. It acts like here it is acting, here it is acting. So from this charge the dipole will tend to move upwards. From this charge the dipole will tend to move downwards. So it creates a torque. When the net force is 0, the torque or the couple is independent of origin. Its magnitude equals to the magnitude of each force multiplied by the arm of the couple, perpendicular distance between the two antiparallel forces. Now we will see the case when P is parallel to E. When this P is parallel to E, dipole has a net force in the direction of increasing field. See this diagram, figure. See, dipole is moving from this direction to this direction. The force is in this direction and here the force is in this direction, and electric field provided is from this charge to this charge. Electric field is in this direction. So E and P are parallel to each other. This is E, this is P. They are parallel to each other. So there is like the field is in increasing force. It is in a increasing. Now when P is anti-parallel to E, the net force on the dipole is in the direction of decreasing field. See over here, the dipole is moving in this direction, electric field is moving in this direction. They are anti-parallel. In this case, the force is inside from here and the force is inside from here. Both the forces are coming to the length of dipole. So in this case, it is showing decreasing field. See, direction of net force opposite to the direction of increasing field. So opposite of direction of increasing is decreasing field. It is along the decreasing field, whereas Direction of net force in this direction, and direction of increasing field is also in the same direction. So they show increasing behavior. Now, in general, the force depends upon the orientation of P with respect to E. How does it happen? We will see in the next slide when we will derive a formula for P, E and torque. Okay, when we will derive formula for all these, we will get to know how this one force is depending upon the orientation of E and P. Force depending upon orientation of P and E. Now we have taken one example over here. The example is of a comb and a paper. The comb polarizes the piece of paper, that is induces net dipole moment in the direction of the field. Further, E due to the comb is not uniform. This non-uniformity in the field makes the dipole to experience a net force on it. Easily seen that paper moves towards the comb. Now we have a comb which we used for our dry hairs. Now this comb got polarized in the sense it got some ions on it. Now we brought small bits of paper which are having very negligible mass near this comb, and they starts getting attracted towards the comb, Why does it happen? Because these charges, these positive or the negative charges which are present on the comb attracts the charges of the paper. They form a kind of dipole here, and as the comb is non-uniform, how we can define a uniformity of the electric field in the comb? It is not possible. It is very much tough to bring uniformity in anything. So a comb with a non-uniform surface, which is a plastic material, will get a non-uniform distribution of charges, and hence the field lines produced by the comb are non-uniform. So this will not create the net force equals to 0 in this system. So there will be some net force which will attract the paper towards the comb and will make the paper stick to the comb. Now the magnitude of torque is given by the force into length of dipole, and the angle by it has like subtended. So QE into 2A sin theta. Force equals to QE, length equals to 2A, and angle is sin theta. Magnitude of torque came as QE 2A sin theta. What is the value of P? That is dipole moment. It is given by 2A Q, 2A into Q. Okay, so this 2A and this Q will be replaced by P. So it will come like PE sin theta. Now if we want to remove sin theta, what kind of product we need to bring over here is tau equals to P cross E, because electric field is E, our dipole moment is, electric field E is vector, our dipole moment is vector. So when we are removing the sin theta component, we can make them a cross product. Okay, so this is what we have got as the value of torque. Now, as I have said, from this formula we will understand how the orientation is important. Tau equals to PE sin theta. Now let us take theta equals to 0, theta equals to 90, theta equals to 180. What is the value of sin 0, sin 90 and sin 180? Sin 0 is 0, sin 90 is 1, sin 180 is 0. In case tau 1, tau 2 and tau 3 equals to PE sin 0, it will give 0. PE sin 90. It will give us PE, maximum torque. Now PE sin 180 degree. It will give us again 0. From this column, what we understand is that whenever P and E, the dipole moment's direction and E's direction is parallel or anti-parallel, 0 degree or 180 degrees with each other, then torque equals to 0. Whereas whenever P, the moment of dipole, and electric field are perpendicular to each other, perpendicular, that is 90 degrees to each other, torque is maximum. That's how alignment of the force, the alignment of electric field, alignment of the dipole moment, everything matters when we define the torque. This will come from this direction. I have explained it, but let's see what the point is written. Its direction is normal to the plane of paper. Okay, this is very much important, as I haven't explained. In this torque minus q plus q, dipole is moving from the from our charges, and E is here perpendicular to this. So the point will be like this. It will come out of, torque will come out of paper. Just see, something is coming out of the laptop screen or the mobile screen you are reading with. So that is the direction of torque when the electric dipole is lying alone with your screen. Okay. The magnitude of P cross E is also PE sin theta, and its direction is normal to the paper coming out of it. Thus, tau equals to P cross E. This torque will tend to align the dipole with the field E. When P is aligned with the field E, the torque is 0. I have already explained. Aligned means it is making a 0 degree or a 180 degree, parallel or anti-parallel alignment, where the torque will be 0. If the field is not uniform, now till up to this point we have went to the uniform electric field. Now we will look like if we don't have a non-uniform, if we are not having a uniform field, we are having a non-uniform. Net force will evidently be non-zero. Of course, like even though we were having uniform electric field, force was still existing there, but now it is non-uniform. Of course, the force will not be equal to 0. Force will not be equal to 0. Let us consider a simpler situation when P is parallel to E or anti-parallel to E. In either cases, the net torque is 0, but there is a net force on the dipole when E is not uniform. Even though like sine 0 degree is 0, sine 180 degree is 0. In these two both cases, what is the value of torque? It is minimum, that is 0. Though the torque is 0, force will exist. Force will not be equal to 0. How can this statement be justified? It can be justified because the field is non-uniform. The field is non-uniform. Okay. So this is the dipole in the uniform and non-uniform fields.